Hello, this is a pre-flight on electromagnetic induction, which covers the second half of the unit on magnetism. Before we begin, we're going to go ahead and review what we've already learned, and that's magnetic flux. The magnetic flux is the field strength, B, times the area of the loop, A, times how the loop is positioned with the field, or a cosine theta function. So to demonstrate, I've taken this magnetic field and I've partitioned it into three sections divided by these red lines. This first section here deals with field strength. You'll see that the top wire, its loop contains many more field lines than the bottom loop. What I've done is I made the field weaker towards the bottom half in section 1. So the flux through this top loop here is much greater than the flux down here. If we go over to the second section, we see that the top loop has a bigger area than the bottom loop, so the flux in the top loop is greater than it is in the bottom. And the third and final one, we see here that this loop of wire is set up to be perfectly in line with the field itself. Therefore, maximum amount of flux can make it through. Whereas here at the bottom, we see that I've gone ahead and I've turned the loop of wire about 45 degrees, so not as many field lines, like you see here, are capable of passing through this one. So those are the three things that determine magnetic flux: field strength, area of the loop, and how the loop is positioned in the field. B, A, cosine theta. So flux itself, though, is not very exciting. In fact, it really doesn't mean much. What matters in the real world is what's called the change in flux. The change in flux, or as field strengths get stronger or weaker, or the areas get bigger or smaller, or the loop of wire is spinning, therefore changing its position, creating change in flux, actually is a very unique consequence. Here is a bar magnet. We have a couple of loops of wire connected to a light bulb. Notice the light bulb is turned off. Nothing special is happening. I'm going to take the magnet and move it towards the loop of wire, and we see that the light bulb lights up. Now there is flux passing through this loop of wire. This is what your field looks like. You see that there are indeed field lines passing through the loop of wire. But since it's not changing, the light bulb goes out. If I pull the magnet away, the light bulb lights up again, because the flux has changed. It went from something to nothing. It doesn't matter if the flux is going from something to nothing or nothing to something. So pay attention to the electrons in this case. When I did this faster, they move faster as opposed to if I move slower. So the faster you change the flux, the more voltage you're actually going to get out of your loop of wire. Also, now if you pay attention to the electrons, see if they go up or down in this front loop. In this case, they went down as the North Pole entered the field. When the North Pole exited the loop, the electrons went up. If I use the South Pole instead, down, up. So not only does how fast you change the flux determine how strong the current and the voltage will be, but also how the flux is changed. Is a North Pole entering the loop? Is it a South Pole entering the loop? What's exiting the loop? These different things will also determine the direction of the current. We're going to use this a little bit later in transformers and generators. But now to give you a quick preview of what the generator is, what we have here is a magnet and a loop of wire. Instead of moving the magnet back and forth, we're just going to spin it. Our mechanism for spinning it is we're going to turn on a faucet. as the magnet spins, it changes north pole or south pole in front of the loop of wire. By changing north pole or south pole in front of the loop of wire, we are changing the flux, therefore providing a steady voltage. The faster I make the faucet pour out, and therefore make the magnet spin, the more voltage I get. In a very crude manner, this is actually how something like the Hoover Dam works. The water flows in, spins magnets, or you could also just spin the coils of wire. You don't have to spin the magnets. The magnets could be stationary, and the coils of wire could be spinning themselves. And as a result, you generate electricity. If you don't need as much, don't have as much water flow through. If you need more water flows through. So the key things to get out of this is 1, learn how to delete stuff. There we go. Key ideas to get out of this. Flux depends on field, which represents B, area, and theta, higher position. Flux itself is not all that important. What really matters is change in flux is. Change in flux creates electric currents. And the other thing about the change in flux is it doesn't matter if you go from high to low flux or low to high flux. However, depending on how you do this determines the direction the current will flow. Also, the faster that you change the flux, the more current you get. Well, that's all I have for you on this pre-flight. Thank you for watching.